Click the bell icon to get latest videos from Ekeeda.
Hello friends, I welcome you all to this video. We have a second video from the fifth chapter for microwave engineering. So in the previous video, we started with the introduction to what exactly the avalanche transit time mean, and we are also introduced to the family members of avalanche transit time devices. So now the very first family member we are going to address in this video. Let us start with reed diode. So here we start with our title. It is reed diode. As in the previous video we have discussed the two very popular modes of operation for avalanche transit time diode or the devices. That is, first of all, the impact ionization avalanche transit time, and the second one, it is trap-at. So it is with respect to the trapped plasma avalanche triggered transit time device here. So reed diode is the first type with respect to the theory of the impact mode of operation. So the reed diode was very first of all invented theoretically by the scientist named Reed in the year 1958. Later on, the practical versions of the reed diode were taken into consideration and they were made available to us. Very first of all, we shall be taking a simple structure of the reed diode in the consideration, and what exactly the biasing type, what are the DC supplies we provide to the terminals of the diode we shall be discussing with. So here we see we can have the three portions into the figures. I can name this to be the figure part A, figure part B and figure part C here. So now, as we know that the avalanche transit time devices are the microwave generators manufactured onto the semiconductor platform. So very popular type of the semiconductor material, we have the silicon into the use. So for the first type, as we have N plus P I and then P plus, this is with respect to the silicon structure. So out of the general types of the semiconductor materials for the reed diode, we have four types here. Very first of all, N plus, that has a junction with the P. The P has a junction with the I, or it is also represented as V, that is the intrinsic type of the semiconductor. And lastly, we have the P plus region. The subscript plus here to that of the N onto the left hand side and P onto the extreme right represent the heavy level of doping with respect to these particular regions here. Now we can see here, as we start from the left hand side, we come across the first junction between the N plus and the P. So in this particular P region, the avalanche multiplication or the avalanche effect is to start over here, and we can say that it is the formation of the high field domain there, and that high field domain must drift from this particular location up to the P plus region onto the right hand extreme. So it has to be through this intrinsic layer represented by I or V, hence this is called as the drift region. Because of the reverse biasing, as we see here, this is the N positive, we apply the positive potential to this particular electrode here, whereas P positive is provided with that of the negative potential. Generally, when we have the P type connected to the positive terminal, N type connected to the negative terminal, we operate the device having the junction into the forward bias condition. And when we reverse the polarities, as like the positive polarity to the N type and negative polarity to the P type, it is the reverse bias. So this is the reverse bias operation with respect to the first junction we come across between the N positive and the P here. Therefore, the avalanche that is to be taken place in this particular P region, because of the heavy breakdown of the charge carriers, we can say here, so we name it to be the avalanche region here. Now it has to be forming the high field domain that will drift through this. That is why we have named it a drift region. And from this junction between the N positive to the P and this one at the right hand extreme having the last P plus here, there it is the mention of the space charge region here. So this is the polarity that we have already connected, positive and negative, to the respective heavily doped N and P type here. And in the device operation, there it is very minimum role of the last region P positive just to collect the high field domain and to get the procedure completed. Hence we call this particular region to be not that much active in the device operation, hence we name it to be the inactive region here. Now we continue from figure part A to the figure part B here. So in the figure part B we have a graph. The graph represents on this particular side the entire length of the device substrate, we can say. The length can be denoted by the simple x here as a parameter, and here whatever the electric field, or in terms of energy also you can discuss the electric field with respect to a function of the distance, we can denote onto this vertical axis. So E as a function of x. So x we put inside the bracket here, and we name the figure part B as the field distribution. The existence of the minority charge carriers is represented in this particular diagram. So as we see here, the N-type heavily doped here. For N-type semiconductor material, the majority charge carrier is the free electron. The electrons are having the negative polarity, while the minority carriers are the holes here. Hence, the existence of the hole having the positive sign inside a circle is representing here corresponding to the N positive region. Then on the another hand, we have the second region to be the P-type. So in the P-type, the majority charge carriers are the holes and the minority charge carriers are the free electrons here. With respect to the doping level of P to that of the N positive, we have high doping level onto the left hand side. Hence, as a part of representation, we have represented the 3 holes onto the N positive and only 2 electrons in the region with respect to P here. Next to that, we have the intrinsic layer. In the intrinsic layer, there it is no majority charge carrier or the minority charge carrier. At the equilibrium condition, we have the equal presence of both the charge carriers. So therefore, we don't represent either the negative signs or the positive signs. And lastly, in the P plus region, we have the negative signs with respect to the free electrons as the minority carriers here. Now, as we have the reverse bias connected to the 2 ends of this device, we have the reverse bias making the most energy level at the junction place. Hence, as far as the field distribution is concerned here, there it is a sudden change at this particular junction with respect to this E as a function of x here. So it has a maximum level, and as we go through this P region, it has come to this particular level that has a constant region throughout the intrinsic. Here we calling it to be the drift region, and finally for the P positive at the right extreme, it has again dropped down here. So this is the field distribution. Now after discussing the figure part A and figure part B, let us have a discussion with respect to the lower figure, that is figure C here. So in this figure C here, again we have the graphical representation. Onto the horizontal axis, we take again the measurement of length in terms of micrometers here. So now we can start from the 0, then we can have the 1 unit here, 2 units here, 3 units here, and now we can have the doping profile on the vertical axis. So here we can have the heavy doping onto the N positive and P positive regions. That is why we have these most heighted columns in this particular diagram at the left extreme and the right extreme. So the doping concentration level is of the order of 10 to the power 20 here. Now in between N positive and P positive, we have this intrinsic and this one to be the extrinsic type. So for extrinsic type, we have more doping as compared to the intrinsic. Hence we have this particular region having of the order of 10 to the power 16 charge carriers per centimeter cube, we can say, as we consider the volume of the one unit. Next to that, for this particular intrinsic level, we have the doping concentration of 10 raised to the power 13. So this is with respect to per cube here. Now in this diagram, the figure portions part A, part B and part C, I hope are very clear. So having the reverse bias there, it will be the avalanche effect into the p-type region, and whatever the high field domain it will be, it has to drift throughout this intrinsic region. So as per as the distance as we have taken on this particular axis representing with the help of x, or in terms of micrometers also, these both are the distance axis. So onto the distance axis, with respect to the intrinsic region, we mark capital L as the maximum length the high field domain has to travel. So there it is, a drifting of the high field domain from this position up to this position. So it will be having a drift velocity also. So now considering the drift velocity and the drift length as shown into the diagram here, we can have a simple formulation with respect to the transit time taken by the charge carrier for the device operation in our diode here. So therefore we can represent here transit time by tau, and it is given as a ratio of the drift length capital L with respect to the drift velocity denoted by V suffix d here. Now along with this transit time represented as the ratio of L to that of the drift velocity Vd, let it will be the equation number 1. We have one multiplication factor with respect to the avalanche operation that is represented here by capital M here, and capital M is computed as 1 divided by, in the denominator we have 1 minus in the bracket capital V minus capital V suffix B, and this bracket is having a power small n here. We can name it equation number 2. So in this equation we have the variables used to determine the multiplication factor for the avalanche operation, that are capital V, V suffix B and small n here. So here capital V represents the applied voltage. So I mention here applied voltage to the device or the diode you can take. Next to that we have the representation of V suffix B. V suffix B represents the breakdown voltage, that is very necessary as we are operating our device into the reverse bias. Hence I mention it to be the breakdown voltage. And lastly, the small n that we have represented as a power to this particular bracket. So small n is the integer value. Mostly the value ranges between 3 to 6 here, and the value of the small n depends on to the doping level of the P positive region, N positive region that are the part of this particular diode. So next to the equation for the multiplication factor with respect to the avalanche operation, we can express the breakdown voltage VB as, so we express the magnitude form, hence we represent mod of VB. So mod of VB depends on several of the factors. The very first of all, that it is rho suffix n in multiplication to the mu suffix n. Again we have in multiplication with respect to the epsilon suffix s. Next to that we have here mod of E max that has been squared and we have a suffix b representing the breakdown condition here, and this is all divided by 2 here. Let this new equation we can name by equation number 3. So in this equation we have the parameters represented onto the right hand side. We can express the meanings as, here we write, where very first of all we have rho suffix n that represents the resistivity of the semiconductor material here. Next to that we have the representation of mu suffix n. Mu suffix n is representing the electron mobility in the corresponding semiconductor field. Next to the electron mobility, we have the next parameter represented here, that it is epsilon suffix s, and epsilon suffix s is the permittivity of the medium. Here the material medium is a semiconductor, hence I write here semiconductor permittivity, which is mostly measured in terms of farads per meter. How much permissible a certain medium to the flow of conduction of electricity is there, that has been measured in terms of this particular constant value here. And lastly we have the representation of E suffix max, that it is the maximum breakdown of the electric field. So electric field I simply represent by capital E here. Now as we have seen the formulae with respect to the various parameters, and the last formula was with respect to the breakdown voltage for the device operation here. Now if we take the breakdown voltage considering the different levels of impurities, now I can say, as we have the different doping levels into the 4 different regions that have been connected in this particular device, so therefore we can have a plot as this. So in this plot, onto the horizontal axis we take the doping concentrations and we can represent it as impurity. So I must say this is impurity density, and this is in terms of per centimeter cube. We can mark the values 10 raised to the power 14, 10 raised to the power 15, 10 raised to the power 16, 10 raised to the power 17, and 10 raised to the power 18. On the vertical axis we take the breakdown voltage represented here. So I represent breakdown voltage by the symbol capital V suffix B, that has been measured in terms of volts simply. We start here on the vertical axis right from 1 at this particular place. Next to that we achieve 10 volts at this particular level. We go up to 100 and finally up to 1000 volts in this particular plot. Now we see the 4 curvatures corresponding to the different types of the semiconductor materials under consideration. Very first of all we represent the curvature with respect to the semiconductor gallium phosphide. After gallium phosphide we can also make the use of the semiconductor material, that is gallium arsenide. And after gallium arsenide we have the very popular semiconductor materials that are the silicon, and next to that it is the germanium. Now in this plot if you see here, if we go on increasing the impurity density, that means if we go on increasing the doping concentrations into the extreme semiconductor regions into the device diode, that time the breakdown voltage will be of lower order. And if we don't have much of the doping concentration or the impurity concentration, that time we have to go for higher order of the breakdown voltage, and after that the avalanche multiplication, the avalanche effect will be in operation of the device here. Now we discuss the very important topic for this particular device, that it is how exactly the negative resistance is obtained. Because as we are very much familiar that if we are going to work with that of the microwave tubes, we have the velocity modulation as the operating principle, so that the microwave energy can be generated, and onto the semiconductor platform, either it may be the transport electron devices or now the avalanche transit time devices, we should have the device operated into the negative resistance mode. So now how exactly the negative resistance is achieved in this particular diode, we see along with the help of the next diagram. So in the next diagram, we first of all get back to the structure here. So I mark here this to be the part A of the figure, and this is representing the structure of the diode. As we start here, this is N plus region, this is P region, the intrinsic region represented by I, and finally the P positive region. The drift space that has to be traveled by the high field domain, that is represented by L here. The reverse bias is applied as like the positive terminal to the N positive and negative terminal to the P positive. So here we represent capital V, that is AC type here, and from this particular junction to this particular junction we have a space charge region. So in the part B, we represent the field distribution that we have already discussed. So in the field distribution that has been represented E as a function of x, x being the distance, it has the maximum level at the junction between the N positive and the P here. Now after the figure part A and figure part B, we go for figure part C and figure part D here. In the figure part C, we represent here the applied voltage VAC. So I mention here applied voltage. As it is the alternating voltage, we have the positive half cycle, the negative half cycle, again the positive half cycle represented onto the vertical and the horizontal axis. We can represent the corresponding parameters here. On the horizontal axis, we can take omega t as a function of this particular applied voltage here. So now if we take omega t value to be equal to 0 when it is at maximum into the positive half cycle, we get the phase value of pi by 2. Then when it come back to the 0 level, it will be of pi. Next to that, at the negative extreme, we are at the phase of 3 pi by 2, and we come to the 2 pi phase when one cycle is completed here. Next to that, again there it is a start of the positive half cycle, and at the positive extreme here we can represent for the every cycle that it is the maximum amplitude of the applied voltage, represented as in the part A figure by V suffix A here. So applied voltage is there. Now there it is the formation of the high field region constituting the current here. Now we know that the applied voltage is at the N positive, which is at the left extreme, and after the avalanche effect that has been taken in the second region of P type, we obtain the current pulse represented into the figure D. So here it is the figure D we show here, and in the figure D we can represent the current values or the simply the current form by I suffix 0 as a function of time t, or for the output we can take the extraction I suffix e as a function of t here. So in this diagram, at the maximum peak we represent I suffix 0 as a function of t here, and whatever the normal value as a constant we see throughout the drift region here, that we have represented I suffix e as a function of t here. And this particular level, because of the drift current, we can represent I suffix d as a function of again the time t here. So time t parameter we have represented onto the horizontal axis. So here in this diagram we can start at 0 onto the left extreme. So as we go on, this is the time duration in which the pulse has been generated. So if we take the help of the transit time in the representation here, so the complete is the transit time tau, we can get it divided by 2 to represent the two halves of this particular pulse. So this is the tau by 2, this is also tau by 2. So as we approach the drifting of this particular pulse at this particular extreme, we come to have twice tau here. So as we started from 0 here. So this will explain you the better how exactly the high field domain will be forming at the avalanche region, and it will be drifting towards the right hand extreme P positive region. So in this diagram, if you can see here, we have the marking of phases here. So this is the corresponding marking at the 0 degree of phase or 0 radians you can take here. So this is the actual time interval t equal to 0 when we have applied the corresponding voltages to the device to operate. So after 0 degree of phase, we are getting the output at this particular position. So if you can see here, after 0 radians, we have come to the pi radians. Here radians can be represented like this. So this is 180 degree out of phase, the output with respect to the applied input. So 180 degree out of phase, it means a reversal. So this we can consider to be the negative resistance device operation. And when the device operation is exhibiting the negative resistance, it is nothing but generating the microwave energy in our case here. Now as we see that at the very first junction between the N positive and the P type, if the charge carrier generated are the holes and that are drifting through the intrinsic layer or the complete drift length represented by L, there it will be a reduction into the field developed with respect to that particular junction location. So taking the help of the Poisson's equation, we can represent the mathematical form as like, we have the differential of dE with respect to dx computed as minus rho divided by epsilon suffix s here. So in this particular equation, we have rho representing the volume charge density. Generally we can also represent it as rho suffix v also. So I mention here volume charge density. As we know that the charge is measured in terms of coulombs. With respect to the volume here, it will be coulombs per meter cube as a measurement unit for this rho v here. And here we have epsilon suffix s. This is the permittivity of the semiconductor material. So this permittivity of the semiconductor material is measured in terms of farads per meter. Now as we see in the device operation, the high field region is generated and we have represented it in terms of the current pulse. So whatever the induced current in the device operation is there, we can represent mathematically as capital I suffix e as a function of time t computed as the ratio of capital Q divided by tau, or we can also express it as V suffix d in multiplication to Q divided by capital L. So in this equation, we can express the various parameters used onto the right hand side as capital Q is equal to the total charge of the holes. So this is the total charge of the holes that is to be moving throughout this drift length. Next to that, we have represented V suffix d in the next form here. V suffix d is the drift velocity for these holes here. And finally, capital L that represents the drift length. Mostly when such a avalanche transit time device is being operated, it is kept inside a microwave cavity. So with respect to the resonance, the frequency can be given by the next equation. We have the relation 2 pi f is equal to pi radians divided by the transit time tau. Therefore, we can express the frequency f is equal to 1 upon twice tau. It can be expressed as v suffix d divided by twice l. So this will be a very simple formula that may be helpful while solving the problems based on to this particular device operation or the others in the same family as the members also. Lastly, we can conclude this particular topic addressing the output power and the quality factor. So expressing the output power, we can show you one equation where the output power is represented by capital P and it is expressed as 0.707 that has been obtained along with a multiplication of VA into ID. So this is measured in terms of watts per unit area. Now this is VA. So VA is the amplitude of the applied voltage that we have shown. So that is very obvious voltage, and ID is the direct current. A multiplication of the voltage and current in multiplication to this constant value gives us the practically obtained output power with respect to this device operation. And finally, we can express the quality factor of the device as omega, the angular frequency, in multiplication to the ratio, where the ratio has numerator representing the maximum storage of energy and the denominator is representing us the average of the dissipated power. So I hope this formulae and the device operation has made the importance of the reed diode in the family of avalanche transit time devices very clear. By the next lecture, we shall be addressing the generalized impact diode in the same chapter. I hope you are getting the details of microwave engineering subject and various topics very well. For more information like this and on to the another subjects also, you can subscribe to Ekeeda channel. Thank you.